This is a video from section 11.1 in a Calculus 2 class. The directions say to determine whether the sequence converges or diverges. If it converges, find the limit. So let's take a look at problem 41. 41 says a sub n is equal to negative 1 to the n over 2 times the square root of n. If I look at the absolute value of a sub n, this is equal to the absolute value of negative 1 to the n over 2 times the square root of n. But we can write this as 1 over 2 times the square root of n. Now, if I look at the limit as n goes to infinity of the absolute value of a sub n, this is equal to the limit as n goes to infinity of 1 over 2 times the square root of n. But I can pull the 1/2 out in front of the limit, and so I can write this as 1/2 times the limit as n goes to infinity of 1 over square root of n. But this is equal to 1/2 times 0, which is equal to 0. And so what that says is the limit as n goes to infinity of the absolute value of a sub n is equal to 0. And there's a theorem in the book that says if the limit as n goes to infinity of the absolute value of a sub n is equal to 0, the limit as n goes to infinity of a sub n equals 0. And so what we can say is that this sequence a sub n converges to 0. And remember, in the beginning we said that a sub n is negative 1 to the n over 2 times the square root of n. Okay, let's take a look at 43. Suppose we have the sequence where the nth term is 2n minus 1 factorial divided by 2n plus 1 factorial. Now, before we address 43 directly, I want you to recall n factorial is equal to n times n minus 1 times n minus 2 times 3 times 2 times 1. And remember, n factorial, this is red. What I'm circling is red n factorial. For example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And that's 120. And you can think of that as there are 120 ways to arrange 5 people for a photograph. All right? 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. And in case people are interested, this is equal to 5,040. All right, now to the problem. So the nth term of this sequence is given by 2n minus 1 factorial divided by 2n plus 1 factorial. But 2n minus 1 factorial is 2n minus 1 times 2n minus 2 times 2n minus 3 all the way down to 3 times 2 times 1. And we're dividing by 2n plus 1 factorial, which can be written as 2n plus 1 times 2n times 2n minus 1 times 2n minus 2 times 2n minus 3 all the way down to 3 times 2 times 1. And so notice, every factor in the numerator here, 2n minus 1, 2n minus 2, 2n minus 3 all the way down to 3 times 2 times 1, can cancel these corresponding factors in the denominator. So notice the 2n minus 1 here, 2n minus 2, 2n minus 3, all the way down to 3 times 2 times 1. And what we have left in the numerator is a hidden 1, okay? And in the denominator, we have 2n times 2n plus 1. But this can be written as 1 over 4n squared plus 2n. Now, we want the limit as n goes to infinity of 4n squared plus 2n. But this can be written as follows. This is the limit as n goes to infinity of 1 over n squared times 4 plus 2n over n squared. So I factored out the highest degree in the variable raised to the highest degree in the denominator, essentially. And so right here, this is the limit as n goes to infinity of 1 over n squared times 4 plus 2 over n. And so this is the limit as n goes to infinity of 1 over n squared times 4 plus 2 times 1 over n. Okay, it's subtle, but there's a reason for that, and I'll explain in a second. Now, if it helps to organize it, we could write it this way. We can say the limit as n goes to infinity of 1 over n squared times 1 over 4 plus 2 times 1 over n. But as n gets large, 1 over n goes to 0. And 1 over n squared is also going to 0. And so what we have left is 0 times 1 over 4 plus 2 times 0. But this is 0 times 1/4, which is equal to 0. And what that tells me is that this sequence a sub n converges to 0, where a sub n is 2n minus 1 factorial divided by 2n plus 1 factorial. So that's how 43 works. What I want to do is I want to take a look at problem number. Let's take a look at problem 61. 61 is very subtle, right? Now, this is a sub n is n factorial divided by 2 to the n. This one's tricky, all right? So if I have n factorial over 2 to the n, this is n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. I'm going to divide by n copies of 2 multiplied together, basically. So I have 2 times 2 times 2 times ... times 2 times 2 times 2. All right, this is what I'm going to do. I'm going to break this apart. So I have n over 2 times n minus 1 over 2. I want you to look at this in a very deliberate way, all right? Times n minus 2 over 2 times n minus 3 over 2 times 4 over 2 times 3 over 2 times 2 over 2 times 1 over 2. All right. Now, I want you to pay attention to, we could even go here, if anything. Look at 3 over 2. 3 over 2 is bigger than or equal to 1.5, right? Because 3 over 2 is 1.5. But that means every factor that comes to the left, right? of 3 over 2 will be bigger than 1.5 completely, right? So in other words, when I look at 4 over 2, this is bigger than or equal to 1.5. When I look at n minus 3 over 2, this one is bigger than or equal to 1.5. When I look at n minus 2 over 2, this one is bigger than or equal to 1.5. When I look at n minus 1 over 2, bigger than or equal to 1.5. And when I look at n over 2, this is bigger than or equal to 1.5. Now, why did I want that? Because I claim this is bigger than or equal to 1.5 times 1.5 times 1.5 times 1.5, and I'm going to go dot, 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 times 1.5, right? Times 1.5. Now, 2 over 2 is the same as 1, right? Times a half. Now, altogether, there's n factors. That's what we have altogether. But I'm going to remove the 1 and the 1/2 from that, right? And so what we have, I claim, is 1.5 to the n minus 2 times 1 times a half. Now, look at this. What is the limit as n goes to infinity of 1.5 to the n minus 2, right, times 1 times a half? Well, I claim that's going to be infinity. But if I look at n factorial over 2 to the n, this is greater than or equal to 1.5 to the n minus 2 times 1 times a half, right? So, therefore, the limit as n goes to infinity of n factorial over 2 to the n must also be infinity. And what that says is that this sequence A sub n diverges. That's a really, really great question. Now, let's go over that again. So A sub n is equal to n factorial over 2 to the n. Now, notice that n factorial is n times n minus 1 times n minus 2 all the way down to 1, if we continue in that pattern. 2 to the n is equal to 2 times 2 times 2 all the way down till I reach n copies of 2 multiplied together. So I have n copies of 2 multiplied together. That's how we represent 2 to the n. Okay? Now, again, let's back up. Let's make sure we understand this. And I want you to notice something. I was able to pair up a factor in the numerator with a 2 in the denominator. That's important. So I want you to notice something. I was able to write n over 2, right, times n minus 1 over 2 times n minus 2 over 2, and I continued in that pattern until I got 3 over 2 times 2 over 2 times 1 over 2, right? Now, the claim is each one of these factors up to 3 over 2 is bigger than or equal to 1.5. That is fact, right? Now, this is greater than or equal to 1.5 times 1.5 times 1.5 all the way down to 1.5 times 1 times a half. Because remember, 2 over 2 is the same as 1. Now, remember that there were n copies of 2 at the bottom. So there's n factors that we're dealing with. And every factor in the denominator got paired off with a factor in the numerator. And so here are 2 factors, correct? But what do I have to add to 2 to get to n? And I have to add n minus 2, right? That's how many factors are here. And so if I take n minus 2 copies of 1.5, I end up with 1.5 to the n minus 2 times 1 times a half. But when I took the limit as n goes to infinity, that has to be infinity. And if you notice, n factorial over 2 to the n is greater than or equal to 1.5 to the n minus 2 times 1 times a half. And therefore, that's what's showing, that's how we can show the limit as n goes to infinity of n factorial over 2 to the n is infinity. And thus, this sequence diverges. It's a good problem, by the way. I want to show you one last question. If we take a look at 50, suppose a sub n is the nth root of 2 to the 1 plus 3n. But this can be written as 2 to the 1 plus 3n raised to the 1 over n. But this is 2 to the 1 over n times 1 plus 3n. So when you have an exponent raised to another exponent, we multiply those exponents, right? But this is 2 to the 1 over n plus 3. Okay, we're almost ready. If I take the limit, so we'll go over here, as n goes to infinity of 1 over n plus 3. This is 0 plus 3, which is 3, right? So this is what I do. I look at the limit as n goes to infinity of a sub n. This is the limit as n goes to infinity of 2 to the 1 over n plus 3. But this is 2 to the limit as n goes to infinity of 1 over n plus 3, which is 2 cubed, which is equal to 8. And so, therefore, this sequence a sub n must converge to 8. And that's how we do problem 50. And that's probably a good stopping point for this video. This is a video from a section 11.1. We did problems 41, 43, 61, and 50. Thank you.